So we've talked about the constitutive relation between stress and strain rate, between viscous stress and strain rate. So the relation was this was the relation. So this is your viscous stress or deviatoric stress. This is your coefficient of viscosity. This is known as bulk viscosity. So all other terms were explained to you. Now I had also told you that divergence of stress results in net force. So divergence of stress is tau ij, comma j. This is known as divergence of your stress tensor. So you have got the expression 2 mu ui comma j plus uj comma I. This is a strain rate plus lambda delta ij. This is your divergence of velocity. So this is equal to ui comma I. So you have to find comma j of this. Can you see what I have done? I have replaced strain rate by this term ui comma j plus uj comma I. This is del ui by del xj. This is del uj by del xi. So these are derivatives of velocity. And divergence of velocity is ui comma I. If you expand it, del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3. And we have to take derivative with j. This was our tau ij. So shear stress has two, this viscous stress has two index I and j. So both are represented here. So this is a scalar quantity, while delta ij is there to take care of this ij. When you have got normal stresses like tau xs, only then this term is non-zero. If you have got tau xy, then this term goes to zero because I and j are different. Any questions about this? You have to practice it out. It's not a big deal. Now we have to take its derivative. Now mu is a constant, so mu will not get affected. You have to take the derivative of this with j, so it becomes ui comma jj plus uj comma ij. Simple derivative plus lambda delta ij ui comma I. You have to take the derivative with j. Simple differentiation. Now you look at this. This is mu ui comma jj plus Look at this term uj comma ij. Here ui comma ij. So you see here you have a delta ij. So you can make one index same. If you make I is equal to j, then what happens? So what you see here I comma ij, and here if we just make I is equal to j, what do you get? If I is equal to j, delta ij multiplication means you have to just equate I and j. So what do you get here? And you say this is, we generally don't like to make all three indices same. And since this I and I, you can replace by any other index. So I and I you can replace by any other index. It's a dummy index. It doesn't matter whether you call it I or M. And here you have got delta ij. So you can replace it by mi. So you are left with lambda
So can
un comma mi.
so can you explain this again, sir? I couldn't get that how the M replacement is same as I.
Look, something is a dummy index. So it can have any name. Instead of I call it M. Like this was divergence of velocity. So this I, now the problem here was you have another I here. And generally we don't like more than two same indices. So here instead of I could have written M.
Okay, sir.
Okay. So it now it represents, it is like a scalar quantity. Um comma m is a scalar quantity. You want this derivative with j. So now you see j here is having all 1, 2, 3 values. But you allow, since it is delta ij, is- you see here there is an index I. So it represents force balance, force component in I direction. J comma j is a dummy because it is repeating. So net force in I direction is given by tau ij comma j. Now this index, you see here both are there, I comma j, j comma I, and you have taken derivative with j. So now j becomes dummy. Only effect is left on I. So we want force component in I direction. So we are getting a term in I index. Similarly here, since j is repeating and it is delta ij, so you can knock out j, replace with I. So this is what we are getting. So this becomes mu u I comma jj plus. There is another term here, mu uj comma ij. Now let's see j comma ij, and here you are having m comma mi. So this term you can replace with uj comma ji. Equality of partial derivatives. Uj comma ij has to be equal to uj comma ji. Otherwise the partial derivatives are not defined. Now you see these two terms are same. J is a dummy, m comma mi. So you can replace this term with lambda plus mu u j comma ji. Any problem? These two are same. Um comma mi, uj comma ji, they are same. So this is, what is this term? Ui comma jj. This is known as Laplacian of u. And this is what? Gradient of divergence of velocity. Can you see this?
Yes, sir.
Excuse me, sir. So
Yeah.
how did you replace U J I J with U? Sorry, sir. U J J I U M M I with U J J I.
You're saying here?
Yes, sir.
From where you want the change? Look, I is a dummy index. You can call it m instead of I. And this delta ij, I have replaced delta ij into j. So one has to get knocked out. So I equated I equal to j and replaced j with I.
Okay, sir.
Basically
Okay,
here I should
understood.
have replaced, we should have called it m. Now there won't be any confusion. Since it is a scalar quantity, um comma m is a scalar quantity. Divergence of velocity is ui comma I. You could have written um comma m, anything. It is basically del u1 by del x1 plus del u2 by del x2 plus del u3 by del x3. All three terms are there. So this I and j I'm using here, so I should not have used I here. Now is it all right?
Yes, understood, sir. Thank you.
So you get the net force due to viscous stresses. Now if you write the equation of motion, rho dv by dt is equal to minus gradient of p plus gravitational force plus F viscous. This is the viscous force. U and V are same. Basically, whenever I'm putting a bar, it means it's a vector. I'm not talking of component. Component I'm replacing by UI. So this becomes your equation of motion. If your flow is incompressible, this term goes away. So this will go away. So you'll be left only with this term. And you see what does this term look like? Can you recognize this term? What is this del square? So this means del square u by del x square. So this is the first term. When you expand del square v. Second term is similarly you have the third term. Where have you seen this kind of an expression? Anybody? In heat conduction, you have seen this. So what is this expression? Del square T by del x square. So this expression was there. Probably you've not done heat conduction so far, but in somewhere in 12th standard.
सर ये लैप्लासियन ऑपरेटर में किया था सर.
Yeah, this is
तो
Laplacian.
श्रोडिंजर्स वेव इक्वेशन में किया था.
Okay, so this is Laplacian. So you see, so this heat diffuses away. This is heat diffusion. Because of thermal gradients, you have got heat flux, and this represents diffusion of heat. So this is the diffusion effects because of viscosity. Okay. Now see what happens. You have a fluid flow. So there are layers which are moving with different velocities. So there is a velocity gradient. Suppose this is a slow moving layer. This is fast. So this fast moving layer will try to drag it along. Will tend to increase its speed. So this speed increase happens because there is friction between the layers. The friction will try to drag it along. It will tend to increase its speed. If there was no friction, these fellows will be moving with their own speeds. Because of friction, this will tend to slow down, this will tend to increase its speed. So you see, there is a transfer of momentum in the perpendicular direction. These fellows tend to gain momentum because of viscous effects. Also, there is some energy transfer. So we'll write equation of mechanical energy. How mechanical energy is transported due to viscous effect. And viscous effects also cause dissipation of energy. Why do they cause dissipation of energy? One thing is it is transferring energy because it is increasing its speed. Macroscopic speed is increasing. So that is energy is going from one layer to another layer. But how dissipation of energy occurs? Because of viscous effects.
So because the molecules then with the neighboring molecules they interfere and that creates that.
So there is also increase in molecular motion. So you can say there is increase in thermal motion of the molecules because of rubbing each other. So not all the energy is transferred in macroscopic manner. Some energy goes into microscopic kinetic energy. So that is your thermal effect. You will say your temperature will rise, things like that will happen. Okay. So first we will do how the mechanical energy gets transported. Then we'll talk about loss of energy or increase in temperature because of viscous friction. Now again we write the equation of motion. So this was the equation of motion. Now if we take its dot product with velocity, so we saw in the last class how if there is an unbalanced force, it leads to generation of kinetic energy. So same thing we want to do. So I have taken dot product with velocity. Here, instead of writing like a dot product, I have written Vi. Now you see this is force in I direction, tau ij comma j. So I multiplied with Vi. So it is looking like velocity dot so this was your net force per unit volume due to these viscous stresses. You have taken dot product with velocity. Now what is this equal to? Can you write like this?
Yes.
So this is nothing but half V dot V. If you take its derivative, you will get this term. Now this is V dot rho G. Now you can replace G as minus gradient of some potential phi. So this we had done earlier, like phi is equal to Gz, suppose. Then your gradient of phi will become G and minus gradient will be minus G. So here you have a direction. So that is why you are writing minus gradient of phi. Now if you say it's a steady potential, what is the meaning of steady potential?
It
Well,
remains uniform.
yeah, it doesn't change with time. You see, gravitational force doesn't change with time. So you can write del phi by del t is 0. Okay. So what you can do now? Now what is d phi by dt? Del phi by del t plus velocity dot gradient of phi. So phi was gz. Okay. So this is d del phi by del t is 0. So v bar dot gradient of phi, you had rho g bar, you write rho g bar, so you get gradient of phi is nothing but g. Gradient of phi was g. So rho d phi by dt. So you can write something like this: v dot rho g. So this term is nothing but rho d phi by dt, and you have got other terms. So you can take this term onto the left hand side. Just check it out. There is a minus sign also. Rho d by dt of half this is equal to can you see what has happened? I just converted this term into a potential. So it is derivative of potential. So it is just total time derivative of your kinetic energy plus potential energy. And this can be written as minus v dot gradient of p plus this. So because of pressure effects, some energy is transferred. Similarly, because of net force due to viscous stresses, some energy is transferred. Any problem? Whenever there is any net force, it will lead to generation of kinetic energy. So this is your mechanical energy. Kinetic plus potential energy. Its total time derivative will be given by this. So you look at this thing again. This derivation is not difficult. There is some messing with signs. Nothing much. Okay.
Yes.
Now let us go to the energy equation. So you see there is law of conservation of energy. So what is first law of thermodynamics? So this is work done. This is heat transfer. This is your total energy. And what is the total energy? You have got internal energy. Let's call it E plus. This is the potential energy. This is the internal energy. So you have got all the parts: internal, kinetic, potential. So you multiply it with mass. So this was all per unit mass. For finding the total energy, you have multiplied with the mass. If you want its total time derivative, So what you will get? You see, mass is conserved. So its time derivative, you can treat it as a constant and take it out. Is it all right?
Yes, sir.
Okay. Now we have to find this work W dot. Okay. So what we do? We first take a volume. So I have taken a simple case. So what is the velocity here? V1. What is the velocity of the fluid here? V1 plus del V1 by del X. Okay.
Yes.
So we have just taken one stress. So what is the work transfer due to this? Power transfer. Here you see there is a these are in different directions. So it will lead to minus sigma xx V1. And this is both are in the same direction. So you'll get sigma xx plus del sigma xx by del x dx V1 plus del V1 by del x dx. Okay. And you also have to multiply it with the areas. Area of the face. If this is dx, so you are multiplying with dy dz. Okay. Because force into velocity is power.
Yes,
Now
sir.
if you find it, this minus sigma x v1 will cancel out. What you will get? Sigma xx. And you multiply with delta v1 by del x. Similarly, plus del sigma xx by del x into v1. And multiplication of these two terms, you have a dx square. So this is of a much smaller order, you can neglect it. And this entire thing gets multiplied by dx dy dz. So the entire thing you can write as sigma xx v1 comma del x into volume. Dx dy dz is nothing but volume of the element. Sigma xx into v1. So you've taken a if you just take derivative of this with x, sigma xx derivative with x into v1 plus sigma xx del v1 by del x. Is it all right?
Yes.
So you can replace the entire term So this is something nothing but of this kind. So you can replace the entire work done by this term due to your stress tensor and velocity. And there is another heat flux vector. This is a heat flux. Heat transfer is divergence of heat flux vector. You have got some heat transfer here, Qx. Heat is also leaving this place. So what is leaving is Qx plus del Qx by del x dx. So you will find that net heat flux is del Qx by del x. And it is occurring over a surface area. So this will be the per unit volume heat flux from this volume. So because of heat conduction, this is the net loss of heat from this volume. So that we write as Q dot. So what is the equation of energy balance? Rho d by dt, internal energy plus kinetic energy plus potential energy equal to minus divergence of Q. Now you are taking terms per unit volume. You see, this is also per unit volume. You are not multiplied with volume. Plus divergence of. Is it all right? You have got energy transfer due to stresses, loss of heat due to heat conduction. Now this, what is this stress? Is equal to minus P. This is a viscous stress. This is a hydrostatic stress. This is a full stress. Okay. Please switch off your mobile. The divergence of sigma V is equal to divergence of minus PV plus divergence of so this thing you can write as whatever is above. So what do you get? This thing you can say is, we will check it. So this becomes can you see that this is all right? Okay. So I replace this with divergence of ETV. This is standard Gauss theorem. This was like a flux over the surface. If you integrate, you can convert it into a integral by divergence. Okay, we'll check it out. Then we have just collected the divergence terms. You see, everywhere there was a divergence. So P plus rho ETV plus Q minus this. So all divergences, they were all already divergences. Only here we made divergence of this term also and took it to this side. What I think is there should not be any gradient here. So Et dot Vn, that represents the flux leaving the surface. After integral, you get divergence of ETV. Now it is fine. Now you see there is one term here, divergence of tau V. Now this equation we have got, if we, you see we had earlier written an equation of mechanical energy. Let me write it again. So this was one equation we had written. Then the second equation becomes, so if we subtract 1 from 2, you see what happened? We subtracted out the mechanical part, half v square plus phi, and we were left only with internal energy. So it was minus divergence of Q. So this term remains plus phi. If you just subtract it out, you will see only these remain. And what is phi here? Phi is the dissipation function. So this is a dissipation function. If you expand it, you get 2 mu
Excuse me, sir.
Yes,
Sir, is it in our syllabus also dissipation function?
I will get to it.
Oh,
So you see, all these terms are positive. They are all squares. Only this is the negative part. And if the flow is incompressible, this will also go to 0. So what we are seeing is how you can change internal energy. So this internal energy change is happening because of heat transfer, work done by pressure. You see, pressure into divergence of velocity. If there is any change in volume, so this term will contribute to the work transfer. So all this will lead to change in internal energy plus dissipation function. You see, this viscous effects cause dissipation. So, and you are converting macroscopic energy into microscopic energy. So that is where you get the terms which are leading to change in internal energy. If it was this isothermal case, there was no change in temperature, then what will happen? Your internal energy doesn't change if there is no change in temperature.
so then there will be no dissipation function.
So then, so that becomes an idealization. You are neglecting heat transfer. You are
Yes.
kind of going to ideal fluids. Okay. So that doesn't happen. So in reality, you will have change in temperature. There will be thermal effects. So just I have explained how you convert kinetic energy into thermal energy. So that's the only importance. You can just check it out, these expressions, okay, whether you're getting the same thing or not. Now you know the entire machinery of generating these expressions. Okay. So class is over for today. If you have any questions, we will see later. Next week we can kind of review what we taught till now. Okay. So class is
Thank
over.
you, sir.
Excuse me, sir.
Yeah.
Sir, that the paper that we have to write on the history of developments of fluid,